Hi, I'm Mike Barnes and welcome to this video about research at the University of Manchester. The project we're looking at is examining managing future electrical networks and in particular how we might protect them. The project is interdisciplinary and involves a number of younger researchers. In the 21st century, the UK will have to move away from using fossil fuels to power its economy. Instead, we'll use a mix of sources, including offshore wind. In 2016, already 12% of our electricity came from wind. That's more than from coal. Presently, wind farms are small and nearshore, like Bank behind me, but in future they'll be larger and thus have to go much further out to sea, out of sight of land. This means the technology to bring the electricity back to shore will need to be more advanced. Onshore electrical power systems use alternating current, or AC. This falls to zero 100 times per second, and if you're breaking current, this is a good place to break it. Offshore, you use direct current, or DC. This doesn't fall to zero and makes breaking current far more difficult, so advanced breaker concepts are needed. A whole variety of concepts have been proposed, but they're still being evaluated. This project was started to evaluate them for the UK, to work out what are best value for the UK bill and taxpayer. To that extent, we're evaluating system components, we're looking at the underlying physics which constrains the operation of such systems, and we're examining new technologies which may change the way such breakers operate in radical ways, such as superconducting technology. And the prototypes of these concepts have been evaluated in the university's high voltage labs.
We have here the various components of the DC breaker. We can see here the superconducting coil, which is made from magnesium diboride superconducting wire. We put this coil into the cryostat that you see behind here, which is filled with liquid nitrogen, and this will take the temperature down to minus 250 degrees C, at which stage the superconducting coil will start to superconduct. This coil is then connected to the mechanical switch that you can see here, and at the same time we have a high power electronic bypass circuit that you see on this side here. When the fault current comes on, the superconducting coil will push the current into the bypass circuit, and that will allow us to open the switch here and isolate the fault. That's how the system works. Clearly this is just a laboratory demonstrator. The next step will be to commercialize the whole system, and this will involve quite a lot of industrialization of the various components that you can see here on the bench.
For HVDC breaker operation, very fast-acting actuators are required. The most common actuator used in an HVDC breaker relies on the Thomson Coil principle. The Thomson Coil consists of a metallic armature and a spiral coil. When we excite the coil with a time-varying current, this time-varying current produces a time-varying field. This time-varying field interacts with the metallic armature, inducing eddy currents in the surface. Due to the direction of the inducing eddy currents, a very strong and repulsive force appears between the coil and the moving element.
We've been investigating the design of the breaker using advanced simulation and testing. We've modelled different breaker concepts using three-dimensional electromechanical software and looked at improving the layout and topology. So, extending the usual one-sided Thomson Coil type actuator to two sides. This can improve, for example, the energy efficiency of the actuator, and since it needs to sit at 500,000 volts above ground, getting energy to it is important. In this, we're using the software at the limits of what it is designed to model, so we need to do some experiments to check it and our ideas. For example, we use a high-speed camera to check the behaviour of the actuator plate. We're building on Britain's great engineering legacy, and this project will be used to inform utilities, government and manufacturers about the potential for this exciting technology.